Okay, so imagine this for a second, right? You're holding like a tiny cup of water, and it's from the ocean. You wouldn't look at that cup and expect to find like a whale in there, would you?
Right, right.
But obviously that doesn't mean the ocean's empty, right? It just means you've got a tiny snapshot. And that's kind of what we're dealing with when we talk about searching for life beyond Earth. It leads us to this really interesting concept, the Fermi Paradox.
Yeah, and what I find so fascinating about the Fermi Paradox is that it really highlights the seeming contradiction we've got. We have this massive universe, right?
Huge.
And yet we haven't found any signs of our cosmic neighbors. It's kind of strange when you think about it.
It really is. It's like you look up at the night sky and you see billions and billions of stars, and it's like, where is everyone? Statistically speaking, with that much space out there, someone should be sending out a signal, shouldn't they?
That's exactly the heart of it. The universe is ancient. I mean, it's way older than our planet. And even if we say life emerging is a super rare event, with enough time and enough planets, it just seems like statistically it should have happened somewhere else too, doesn't it?
It makes sense when you put it like that. So how do we even start to unpack this paradox? We've got some fascinating material to dig into today.
Absolutely.
We've got excerpts from a text conversation and then this paper, Dissolving the Fermi Paradox. Where do we even begin?
Well, that text conversation we have actually gives a pretty clear and simple definition of the Fermi Paradox that I think is a great starting point. It basically boils down to the idea that the universe is so incredibly vast and so incredibly old that it just makes sense that it would be teeming with alien civilizations. But the paradox is we've got zero hard proof.
Right.
No signals from other civilizations, no spaceships, no evidence of galactic empires. It's weird.
It's the ultimate cosmic mystery. So we've got this mind-blowing possibility of a universe that's bursting with life, and at the same time we have this eerie silence.
Yeah.
And then, of course, there's the famous Drake equation. And that's the equation that tries to actually calculate the odds, right? It tries to figure out how many detectable civilizations might be out there in our galaxy.
Exactly. It considers all sorts of factors like how many stars are out there, how many of those stars have planets, and then how many of those planets could actually support life.
And this is where it starts to get really interesting, right? Because we're not just looking for planets that could theoretically have life, but we're talking about the chances of life actually starting in the first place.
That's right.
Even on planets where the conditions seem perfect, life still might not emerge. It's almost like hoping to win the lottery, but on a cosmic scale.
It really is.
Yeah.
And while the Drake equation is a great tool, it's important to remember it's full of these big question marks, these unknowns. Think of it like trying to bake a cake with a recipe, but every ingredient is a total guess. We're working with what we know, but we're still figuring out the fundamental rules of how life begins, even here on Earth.
So it sounds like it's more like a cosmic guessing game than a precise calculation.
Yeah, in a way. We're trying to understand the rules of a game that we've only just started to play.
Right. Okay, I'm hooked. So let's dive into this paper because I know it digs even deeper into those uncertainties.
It does, yeah. And I think what's fascinating is that it highlights just how vast those uncertainties really are, especially when it comes to the emergence of life itself.
Okay, let's talk about that. Okay,
Okay.
so we're talking about this recipe for life, right? But it's like some of the ingredients are these big cosmic question marks.
Totally.
We've got the pan in the oven, but
Yeah.
no idea how much flour to use.
Yeah. And the paper does a great job, I think, of calling out a couple of those really big question marks.
Right.
Specifically, it focuses on those two factors in the Drake equation that we were just talking about.
Yeah.
FL, the probability of life arising at all, and then phi, which is the probability of that life eventually becoming intelligent, like us.
And you said these aren't just small uncertainties,
Oh,
right?
no, not at all.
These are like potentially huge unknowns.
Huge. We're talking about unknowns on a massive scale. And what the authors of the paper are saying is that just throwing out a single number for these factors, just guessing, it's like saying we've got it all figured out, and we definitely don't.
Right. Like we've somehow got the instruction manual for how life begins.
Exactly. And we're so far from that. So one of the examples they use, which I thought was really cool, is the whole idea of a biogenesis.
Okay, remind me what that is again.
A biogenesis, it's basically the process of life, actual living organisms arising from non-living matter.
Right. Like the very first spark of life.
Yes, exactly. And what's interesting is that on Earth, it seems like a biogenesis happened relatively quickly after our planet formed.
So we're kind of overachievers.
Well, maybe.
Yeah.
Or maybe we just got really lucky.
Mm-hmm.
The paper argues that what happened on Earth might be a total fluke, not necessarily the norm.
Oh, interesting. Okay. So our planet might be like the outlier.
Possibly.
Yeah.
And other planets out there, it might take them billions and billions of years longer for life to get going, if it even happens at all.
Right, right. Wow.
And then, even on a molecular level, the paper gets into some really mind-bending stuff. They talk about this thing called the Leventhal paradox. Have you ever heard of that?
I don't think so.
It's fascinating. So imagine a single protein, those building blocks of life. Imagine it's trying to assemble itself purely by chance. The odds against that happening, against a protein just randomly assembling itself, are astronomically small, like almost impossible.
Really?
The paper uses this to illustrate just how much we still don't understand about the jump from non-living matter to something even as complex as a protein, let alone a single-celled organism, let alone intelligent life.
It's kind of like assuming that if you threw a billion Scrabble tiles up in the air, they would just magically land in the right order to write a novel.
Exactly. It's not just about time, right? It's about probability.
Yeah.
It might be that those very first steps in the emergence of life, they're the real hurdle, the real bottleneck.
Like winning the lottery, but 1,000 times in a row.
That's a great way to put it. And here's the thing. Life on Earth, we kind of assume that's the blueprint, right?
Right.
But the paper points out there could be countless other paths that evolution could take. And maybe some of them don't even lead to anything that we would recognize as intelligent life.
So instead of a straight line from, primordial soup to humans, it's more like, what, a giant web of possibilities.
Exactly. A choose-your-own-adventure book, right?
Yeah.
With all of these different branches.
I like that, yeah.
And we've only gone down one path.
And the path we're familiar with might be the exception, not the rule.
It's entirely possible. We tend to think of intelligence as this inevitable outcome of evolution. But what if our version of intelligence, the kind that builds telescopes and writes poetry, what if that's the outlier?
Wow, yeah. So not only do we have to consider the chances of life itself emerging, we've also got to factor in the chances of that life evolving in a way that leads to intelligence.
Right.
Which could be a whole other lottery ticket.
Absolutely. And that's what makes the Fermi Paradox so interesting. It's not enough to just think about the possibility of life. We have to think about the probability of intelligent life that we can actually communicate with.
Right, right. Okay, so we've got all these potential paths for life, but then we have no signs of these thriving civilizations, no cosmic beacons, no intergalactic internet. It's what we call the Fermi observation, right?
Exactly. And I think what's really interesting is that observation, it doesn't carry the same weight for every single thing we're looking at. It's like, say you find a deserted island, right?
Okay.
That could mean a lot of things. It could be that no one ever lived there. Maybe they lived there a long time ago and they left. Or maybe something happened. Maybe something wipes them out.
I see what you mean. So how do we take that idea and apply it to the search for alien life?
So we've done things like aiming radio telescopes at the stars, hoping to pick up a signal. We've sent out our own signals too.
Right.
And so far, nothing totally conclusive.
But this paper also gets into the mind-boggling timescales involved here, right? I mean, if there were a civilization out there and they did have the ability to spread across the galaxy, even slowly, wouldn't we have seen at least some sign of them by now?
That's a really, really important point. And that's actually a much stronger Fermi observation, the fact that we don't see any signs of galactic colonization.
Okay.
Think about it. If even one civilization, just one, somewhere in the vast history of the universe had figured out interstellar travel, and even if they were only moving at a snail's pace compared to the speed of light, you'd think the galaxy would be full of evidence by now.
Right. Like, where are the Dyson spheres, right?
Exactly. Where are the massive spacecraft, the megastructures?
It's kind of eerie when you think about it like that.
Yeah. And the fact that we don't see those things, it has much bigger implications than us just not hearing any stray radio signals.
So just to be clear, not picking up radio chatter is one thing, but the lack of any indication that someone, somewhere, has figured out how to live amongst the stars, that's a completely different thing.
Exactly. And here's what's even more interesting. The authors of the paper, they argue that this particular Fermi observation, this lack of colonization, it might not necessarily mean that civilizations inevitably self-destruct. It might point to something way more fundamental, that the real bottleneck, that rarest event in this whole equation, might actually be abiogenesis itself.
So instead of a galaxy full of civilizations that have blown themselves up or used up all their resources, we might be talking about a universe where life itself is the real outlier.
Exactly. It reframes the entire conversation.
Yeah.
It's not so much about why they haven't contacted us, but about how incredibly slim the chances are that anything made it past the starting line of life in the first place.
Wow. So where does that leave us? I mean, are we back to square one?
Well, not really. I mean, we keep exploring. We have to. Every new piece of data we gather, every calculation we make, it helps us get a clearer picture. But it
Yeah.
also, I think, makes you appreciate life on Earth even more.
Yeah.
It really is this cosmic unicorn, this incredibly rare thing in the universe. Well, then, protecting this little biosphere we've got, the only one we know of, it takes on a whole new level of importance, doesn't it?
It's definitely a humbling thought, and it reminds us that we're not just looking for aliens out there. We're also trying to understand our own place in this incredible, vast, cosmic story. A story where life itself, especially intelligent life, might be the most shocking plot twist of all.
It really might be.
Yeah.
But then again, who knows? Maybe someday it'll be us answering that call from a distant world, getting to share the story of how life found a way here on our little planet.
What a thought. Well, that is about all the time we have for today's deep dive. Thank you all so much for joining us as we explored the Fermi Paradox and all of the mind-blowing possibilities of what might be lurking out there in the universe. Until next time, keep looking up and never stop asking questions.